Hello, everyone. This is probably going to be the most difficult lesson, I think, maybe the whole year. Some of you guys may love it, some of you guys may hate it. I don't know if you know, but this is Miss Chang talking, okay? I know we're not together, but we are together. We're in this together, okay? So as I speak to you and narrate to you, I'll show you this picture. So just as we just saw together, the domino effect, right? If you knock one domino, the first domino out, you know the rest of the dominoes that you've set up will fall. And as long as you did everything right, you know every single domino will fall. Okay? And that's kind of the idea of the principle of mathematical induction. It's a hard concept, very abstract, but I think it's kind of fun, and you'll see how proof can be okay. And you know how you've been doing those easy baby proofs in geometry? Well, this is a little bit more advanced than that, okay? All right, so induction. I know your moms and your dads may have induction ovens. It's because the heat is not touching the actual surface. It's somehow transmitted, right? And that's like dominoes, right? The first domino isn't necessarily touching the last domino, but it's implied that with the first one knocked down, that everybody else gets knocked out, including the last piece. So that's kind of induction definition. So in mathematics, here's a definition of induction. So induction, actually principle of mathematical induction, we're going to call that short. We're going to call it PMI. So if I say prove using PMI, that's what I mean, okay? All right, mathematics, a means of proving a theorem by showing that if it is true for any particular case, it is true of the next case in a series, and then showing that it is indeed true for one particular case. I know what you're thinking, what the factor is this saying? So I hope to clarify that for you. Okay? Now, couple of things. When you're proving using PMI, you have to follow these rules that I'm going to give you. Okay, there's a couple of things that you have to show. Okay, so let's go in through that. Are you still with me? Okay, hopefully. So principle of mathematical induction. And every part that I'm going to show you, you must show. It's actually absolutely necessary. You can't skip any of these steps. You know how usually in algebra I say, oh, you can skip this and skip that, but not so here, okay? All right, let's go through this. The principle of mathematical induction. So a couple of things. I'm going to give you the rules, okay? Let P sub n be a statement involving a positive integer n. Let P sub n be a statement involving a positive integer n. Now, what does that mean? If P sub 1 is true, so that you always have to prove that P sub 1 is true. That means it's in dominoes, it's like you knock down the first one. We can't say that the 50th position of the domino has been knocked down if one hasn't even been knocked down, right? So that's what we're trying to say here, okay? All right, next two. The truth of P sub k implies the truth of P sub k plus 1 for every positive k. Then P sub n must be true for all positive n. So I'm going to say here for every positive k, okay? The truth of P sub k implies the truth of P sub k plus 1. That means they're next to each other, right? That means if this is true, if this has been knocked down, and the next one is also knocked down for every positive k, that means then P sub n must be true for all positive n. You're like, what? Don't worry, all this is going to make sense later, okay? So we're going to put all this together and prove. So I'm going to give you some examples here. Find P sub k plus 1 for the given P sub k. So we're practicing what we have to show because this first part is the most difficult. So number 4 says this. In your textbook, number 4, this is section 9.5, okay? I'm sorry, 9.4. Number 4, P sub k is equal to k over 2 times 5k minus 3. So if this is P sub k, then P sub k plus 1 must be what? Easy peasy. You're proving for the next position. You gotta think k plus 1 and k, you have to understand that this is the one that's before this one before this one, or this one is the one right after this one. So that means if this is true, that means the next position also is true. So when we simplify this, sometimes you're gonna become really savvy, where sometimes you shouldn't simplify it, but sometimes you should. So it's gonna become 5 minus 3, which is 2. So sometimes this is gonna be useful, sometimes simplifying it will be useful. You'll see what I mean later. Let's try another case, okay? Number 6. Piece of K, it sounds like I'm saying piece of cake, huh? Piece of K is 7 plus 13 plus 19. It's a series, right? 7 plus 13 plus 6. It looks like it's a arithmetic sequence, right? Series. 7 plus 13 plus 19 plus all the way to 6k plus 1, which means in this case, it's the next term after this guy here. You see the difference between k minus 1 and k is just one difference, right? This implies that this one is before this guy. Or this implies that this guy is the one after k minus 1. So, if this is true, let's also prove that piece of k plus 1 is also true. Okay? 7 plus 13 plus 19 plus ... plus, okay? Now watch this. This guy here, I'm going to say it's k plus 1, because I'm trying to prove that k plus 1 is true. Minus 1, because it's just that guy. This guy, I changed it to here, okay? Plus 1, plus, do it again. Not 6k plus 1, but 6k plus 1, because it's the one after, right? Plus 1. Okay, try to digest that and try to understand and ask each other, okay? Is equal to, I'm going to simplify this, 19 plus ... plus. Here, this all simplifies to simply this, 6k plus 1. Because it's k plus 1 minus 1, which becomes k, so 6k plus 1. Here, 6k, 6 plus 1. So I like to write this as 6k plus 7. Okay? And there is relevance to why this is happening and why I'm showing you this. So just right now, understand how to go from pk to show that pk plus 1, to find pk plus 1. Okay? Now, at this time, I want to stop and have you guys look at page 652. There are some important sums of powers, okay, of integers, okay, formulas. So formulas, okay. So take a look at those formulas for me right now, okay. Some of them you may recognize, some of them you won't, but the formulas look like this. This is all in your textbook, okay. So I know you've seen these before. This one we've already proved, right? We've proved this one here we've proven this one. We've been working with this. This is for arithmetic series, right? This is the sum of all the arithmetic series. This means we're taking the sum of I squared. So 1 squared plus 2 squared plus 3 squared, and we're saying this is the formula that will give us all the sum. Let's say if I went from 1 through 100, I can use this right here. Okay? What about if it's cubed, right? If I take all the cubes and I add it, this is the sum that I get. Fourth, I get this right here. Oh, it's cut off for you guys, huh? So let me finish writing that for you. Oh, can you guys fill it in for me from your textbook? Okay, let's do that. I'll just finish it by writing this guy here. I'll write it with the permanent marker so you see it. It's actually just 1. It's in your textbook. Okay, sorry about the cutoff. And then when you fifth power every value, increasing every integer, then you get this sum here. Isn't this cool that someone has developed this? But what you're going to do is you're going to actually prove these. Not all of them, but you're going to prove a lot of these, okay? All right, so watch out for the second video for examples. I know you're a little bit confused right now and maybe a little bit scared, but don't be scared. It's going to become very easy. See you, part 2.